So this section's all about friction. We don't think a lot about how the world needs friction. So the first question that it asks you is, what would the world be like without friction? When I think about what friction is, and it says the force that resists the movement of the objects, one of the reasons a sander works is because of the friction that's created, right? It's going to sand off the paint because it's resisting that movement, right? And in that resistance, you're getting something that's happening. Friction, there's different types of friction, and it's going to be dependent on the materials, on the weight, on all sorts of things. And so we're going to go through kind of how do we define that. Well, the force is exerted backward on the pavement when you're walking. And then the pavement exerts an equal but opposite force forward. So then traction is the term that we use for friction that makes motion possible, right? And if you've ever not had traction, you understand how very important it is. So then we talk about magnitude. Remember that vectors have magnitude. Weight affects the friction. Why does weight affect the friction? Well, the weight is part of the force, right? The weight and the force of it pushing down. The area of contact does not affect the friction. It doesn't affect the friction coefficient, which we're going to talk about. But how much contact you have does give you the opportunity to have different points of friction. So while it doesn't affect, for example, if you have the car that has a smooth tire versus the tire with a ridge, you have different types of that tire. It's not that you have a better coefficient of friction. It's the same weight of the car. It's that there's more points for the friction to be there. Friction is greater on a level surface than on a sloped surface. Also makes sense. If you're trying to push an object on a level surface or push it down a slope, you're going to find that the friction is different, right? Because you have different coefficients working there. It appears that frictional force may be related to normal force, all right, which is where we get our formulas from. So then frictional force is proportional to normal force. And you have these new notations that we have not seen before, at least one of them that we have not seen. So then, of course, we know this capital F, that means the force of friction. This little guy is the Greek letter mu. It's technically a lowercase Greek letter, the Greek letter mu. That is your coefficient of your friction, whatever type of friction you're talking about. And the reason it's directly proportional, remember direct variation way back when, y equals k times x, that's a direct variation equation. This is a direct variation equation. They're directly proportional, meaning that this coefficient of this friction multiplied by that normal force is going to equal the force of the friction. And then the frictional force is perpendicular to the normal force. Remember, normal force is directly up and down from the object in relation to what it's sitting on. So then the friction is going to be perpendicular to that, which makes sense when you start seeing it in action. So then what is this mu? This mu is the coefficient of friction. This is the notation that's used for it. It's the measure of how difficult it is for materials to slide relative to each other. All right? That is your coefficient. That's what we're going to use to multiply to figure out our force of friction. And then we have multiple types. So when we look at just the magnitude, the coefficient of friction is unique for each pair of materials, right? So if I have sandpaper, even my grade of sandpaper is going to be different on how much friction it creates. Coefficients of friction are determined experimentally. And so when we do these word problems, you're going to see that they used spring measures to figure out how long it takes for it to start moving or how much force it takes for it to start moving. Because these are experimental based on what you have and what it's sitting on. The force of friction also depends on the object's state of motion. Obviously, once you get something moving, it's easier to move. It didn't change weight. The surface that you have it on didn't change, but its state of motion did. And so once you start moving an object, you actually have a completely different coefficient there than when it was sitting still. So let's talk about the first type, kinetic friction. The frictional forces between two objects that are sliding past each other. This is once it is moving. Kinetic is that they are already moving. You still have friction, right? If we didn't have friction, it would be sliding rather quickly, right? But once it starts moving, that is your kinetic friction. The objects are moving past each other at this point. That is your kinetic friction. You'll notice the notation looks the same, mu, except you have this little tiny k. That indicates that that is the coefficient of the kinetic friction. All right? That's going to have its own coefficient. Static friction then is the other type of friction that we're going to talk about. Also the same notation, that mu, but we have this little s there. This is the frictional force that prevents the slipping of two surfaces that are not moving relative to each other. So kinetic is when they're moving. Static is when it's sitting still and you're trying to get it to move. And the friction's working against you. Once it starts moving, you are in kinetic. You are now moving. And it is still friction. You still have friction involved, but you're going to have a different coefficient at that point. All right? It's not as difficult to move something once it has started moving, even though it still has friction. All right, so let's look at some of the properties of kinetic, and they're going to look very similar to the properties of static. It's directly proportional to the normal force on the sliding object, which is going to be true for the other one. It is parallel to the contact surface. It opposes the motion of the system. All right, so what does this mean? This is still a direct variation. We still have that the force of the friction is going to equal the mu of the kinetic. That's your coefficient of your kinetic friction times your normal force. All right, times your normal force. So it's still directly proportional. Parallel, meaning whatever it's sitting on, that's how the friction is going to run, which makes sense. If I'm sliding something across the floor, the friction is going to be parallel to that floor. That's what's going to be working against me, right, is the floor itself. Opposes the motion. Obviously, by the whole definition of friction, is that it is trying to work against what you're doing. If I'm pushing an object across the floor, the friction is working against me. It depends on the materials and the conditions, all right? The materials and the conditions. Like we've said before, if it's ice or pavement, those are going to feel very different because they have different coefficients of friction. It is independent of the relative speed of the sliding surfaces. So relative speed, once it starts moving, it's just that it is moving. That's when it's kinetic. It's independent of the surface area. Independent of the surface area. This doesn't mean that your surface area doesn't affect it at all. It just means that the actual coefficient is not affected by that surface area. But if you have more surface area, you're going to have more points of contact to then have that friction coefficient working against you. So then let's look at static friction. Static friction can vary from 0 up to the maximum value. So this is where you're going to see a little bit different. You have this static friction and this max. The max is going to equal the same directly proportional thing that we've been doing all along. It's going to be that coefficient times your normal force. You'll notice they have the mu with the s and the normal force. But only when the applied is greater than the max will you see something start to slide. All right? So if I am trying to push a refrigerator, chances are good it's not going to move because the friction, unless he's on wheels, which lowers my friction, right? If I have it sitting flat and I am trying to shove it, the force that I can apply to it is probably not going to be greater than the friction of it working against me. However, my friction of this thing that has wheels, the force that I'm applying to this is more than the friction of it. That's why I'm able to move it. And so that's what this means. If you can look at your applied force, the force that you're actually putting on the object, if it is greater than the friction of the object working against you, it's going to move. If it's less than what's working against you, it's not going to move, right? Does that make sense? And so we're going to compare the applied force to the frictional force to see if it's going to move or not. Properties, these look very similar. It's parallel to the contact surface. It opposes the attempted motion. It depends on the materials and condition of the contact surface, and it is independent of the contact surface area. So again, looks very much You'll notice relative speed's not in there because if it's moving, it's no longer static. It is now kinetic. All right, so that's why you don't see anything that has to do with relative. It says a sled weighing 150 newtons rests on a horizontal section of dry asphalt. The sled is pulled with a maximum force of 115.1 newtons before it slides. When the sled is dragged at a constant velocity, the spring scale indicates a force of 101.7 newtons. What's the coefficient of static friction for a tire on asphalt? What's the coefficient of kinetic friction for a tire on asphalt? So we have, and they'll use this when they're trying to figure out, like, did they stop in time? Could they have stopped in time, etc. But the sled is that they're testing it on weighs 150 newtons. So that's the object that's sitting on the asphalt. It's pulled with a maximum force of 115.1 newtons before it slides, meaning 115.1 newtons was the force that they were applying to it that overcame the static friction that was on that thing. And then once it's sliding, they use this term spring scale. A spring scale is exactly what it sounds like. It is a measuring tool that has a spring in it, and it's going to pull, and on that scale, it's going to tell you the force that's being applied to that spring. So it's measuring the force applied to the spring, all right? They make small ones, and this one's obviously a much larger one if they're trying to figure out how much 150 newtons can get pulled, all right? So the first thing they ask about is the static friction, and then they want the coefficient of the kinetic. So the first thing you want to say is, what do I have? I know how much the object weighs. The object weighs 150 newtons. I know the maximum force that was applied prior to it actually moving. That's 115.1 newtons, all right? And then I know what the force looked like when it was moving, the force that was being applied to keep it moving, all right? So I know those three things. So for static, we're going to start with static. Think of the word static, right? Static is when it is stationary. It's when it's not moving, all right? At the point when it started moving, the static friction had to then equal the applied force, all right? That's what had to happen. And so the max force then of the static friction, that's what we're talking about. Once it equals, it's going to start moving. And so this coefficient, the static coefficient, is what we are going to try to solve for. Well, when they told us the point at which it started moving, they told us the static friction maximum, because that's when the static was no longer greater than the force that was being applied to it. All right? And so this first number that they give us here about force is going to be that max force of the static. So that's what we're going to plug in for that. We're going to plug in the 115.1 newtons. We do not know mu. That's what we're solving for. We do know the natural force. Remember, if we know the weight of an object, if we know the weight of the object, which is this force of gravity on it, then we know the natural force is equal and opposite to it. So if the gravity is pulling it down 150 newtons, then the natural force is positive 150 newtons, right? Because it's stationary and it's not on an incline, right? And so we're going to plug that in there. So that's times that 150 newtons. So then how do I solve for the coefficient of the static friction? We just divide. So go ahead and divide and tell me what you get through 4 significant digits there. So for this, you should have gotten in 4 significant digits, 0.7673. That is your static coefficient. So that is the number that's being applied to the natural force, all right, that you have to get to when you multiply those to be able to move the object. All right? It is done experimentally. So they had to take the sled and say, how much force do I have to put on it before it starts moving? And then once it started moving, they recorded that, and they said, oh, the coefficient then is 0.763. All right, so then once it started moving, that measuring tool said, hey, we're actually not applying 115 newtons anymore. We're only applying 101 newtons. Does that make sense that it would be less force to keep it moving? Have you ever moved anything? It's a whole lot harder to get it started than to keep it going. Don't you agree? Right. And so it makes sense that once they started moving, the force on that spring said, hey, it's not taking as much to keep it going. All right. So now what they have given us, when they have given us this force, is they had handed us the force of the kinetic friction. All right. And so now we're moving on to the kinetic. They have actually told us the force of the kinetic friction. That's going to be equal to that coefficient of the kinetic friction times the natural force on the object. And so again, we're going to plug this in. The force of the kinetic friction is 101.7 newtons. We're solving for the coefficient of the kinetic friction. And again, the object's weight did not change. So it is still 150. And once again, you are going to divide and take it to 4 significant digits. So when you take this to 4 significant digits, you should get that your coefficient here is 0.6780. Information. A crate having a mass of 100 kilograms rests on the smooth concrete floor of a warehouse. Coefficients of friction are, that's supposed to be a sub S there, but the static coefficient is 0.942 and the kinetic coefficient is 0.831. A worker is able to exert a horizontal force of 1255 newtons. Can he push the crate across the floor without assistance? So basically they're saying, is the applied force more than the static force maximum? And if he moves it, what's the magnitude of the crate's acceleration? All right, so they're asking us. So the first thing we want to look at then is the static friction. We want to compare that force of the static friction to the force that he's applying to it. All right, so this time around, we do not know the static friction maximum. This is what we do not know. They have given us the coefficient of the static, and they gave us the mass. We need the natural force here. What is that normal force on this object? I do not know the force. They did not give it to me. They did not give me the natural force. They did not give me the weight. They gave me the mass. All right? There's a difference. They gave me kilograms, not newtons, okay? So I do multiply that coefficient, but I need to multiply it by the 100 kilograms times the gravity. Why am I using positive? Well, I'm talking about normal force, which is the opposite of what's happening to the gravity, right? So you don't just take the mass there and multiply it. The formula is the coefficient times the normal force. They didn't give us the normal force this time. They gave us the mass. All right. Had they said something in newtons, we would be set to go and we would put it right in there. So what is the max force on this object? Well, we're just going to multiply. We're going to say the natural force is the 981. We're going to multiply that by the 0.942. The force, the static force maximum that's being put on this object is 923.16 newtons. All right. That's what happens when I multiply it. Well, when I look at how much force he's putting on it, how much force is he putting on this object? This is how much force he's putting on it, which is greater than the static force. Did he move the object? He moved the object. He put more force on it than it was pushing back on him, which means the forces were not balanced. The static force of the object and the force he was putting on it were not balanced. He was putting more on it than what it was pushing back on him, so it was moving. So my guess is they either just used 9.8 for gravity or they used another rounding in the process. So I agree with that. We're going to do that. And he still moved, right? All right, we still moved the object. All right, so then the second question is, well, we now know it's moving. We've said, yes, it is moving. So we would say, yes, he moved the object. The object moved. Now we're just going to tell the acceleration. All right, and so for this, we're going to go back to the forces acting on it equals mass times acceleration. So we're going right back to this one that we have used about 500 times at this point. The sum of the forces equals the mass times the acceleration. The sum of the forces. Now that it is moving, it has two forces acting on it. Prior to this, we have used the term frictionless table or something like that, right? No longer, we have friction acting on it. Friction, however, always works against, right? Always works against the force that's acting on it. So we have the force that you're using to push it and the friction working against it. The force that you're pushing it then, so this is going to be the force that you're causing it to push. Well, that's the 1255. That's what the push is, right? And then we have friction working against it. However, it is not the static friction we saw from that scale. It's going to be the kinetic friction that's working against you now because it is now moving. And it's not going to be as much friction as when it was sitting still. So now this friction that we're going to subtract, because remember it's working against it, is going to be the kinetic coefficient. That's going to be my 0.831 times the natural force, which we know is 981. It's still going to be this guy right here. That's still your natural force, right? Your normal force working against it. So now we have two forces that are happening. Me pushing the box, friction working against me. That is the sum of my forces, right? That equals my mass times my acceleration. Well, what was my mass? That is your kilograms. Mass is your kilograms. If they had given it to you in newtons, you would have to divide out to get your kilograms mass. They gave you the mass here. That's just 100 times the acceleration. So subtract that side and divide by 100 and tell me what the acceleration is on this. Yeah, you should have gotten 4.40 meters per second squared. I am only using 3 here because I used only 3 in my gravity. So, here was just a yes, no. So I really didn't have to, if it had said what is the static force, then I would have put that one in significant digits too. But it was just, this question was actually just a yes, no question. So. In reality, we could do very little in a frictionless world. We could not pick up objects, walk, or run. You would not even be able to sit in those seats. If you've ever tried to sit on something that's slippery, you will understand friction is very important to sitting as well. All right.